Hello everyone, you are welcome to my new unit tutorial, which it will be based on TensorFlow, Keras and Python. In this video we will dive into the world of semantic segmentation. We will explore the architecture of unit and we will learn how to look into colonoscopy polyp images and try to segment polyps in those images. And then we will grab a new fresh image and we will try to use our model in order to find those polyp in a new fresh images. You are welcome to subscribe my channels and look for my other tutorials in the same playlist. Okay, let's dive into a unit architecture. A unit architecture is a type of deep neural networks that commonly used for image segmentation tasks. And image segmentation is a process of diving an image into different parts and assigning a label to each detected part. This is useful in various applications like medical image analysis, where you might want to identify and classify different structures within an image, such as organs and tumor. As you can see, this is a U shape. The unit architecture gets a name from its shape, which looks like U when visualize it as a diagram. As you can see, it consists two parts. There is the left part and there is the right part. Encoder is the part on the left side of the U shape. It takes the input image and gradually reduces its spatial dimensions while capturing important features. This helps the network learn high-level representations of the input image. The encoder follows a typical architecture of convolutional networks. As you can see, this is, for example, has 64 filters, and this one has 128, and this one 256. Basically, it consists of repeated applications of two 3x3 convolutions, each followed by a rectified linear unit, a ReLU, and a 2x2 max pooling. For example, this red cross, a 2x2 max pooling operation with a stride 2 for the downsampling. The decoder, this part is on the right side of the U shape. It takes the feature learned by the encoder and gradually increase the spatial dimensions back to the original size of the input image. The decoder's job is to generate segmentation map that assigns a label to each pixel, indicating which part of the image it belongs to. So the key feature of the unit architecture is its use of skip connections. You can see here, for example, is the skips connections. These connections allow information from the encoder to directly reach corresponding layer in the decoder. This helps the network combine both high-level and low-level features, which can lead to more accuracy in the segmentation results. Okay, now we are ready to start coding, and the first Python program would be dealing with the data, preparing the data. So let's create our first program. We will name it step number 1, load the data. And for that we will go to the Kaggle website. And let's look for our dataset. It's called CVC Clinic DB. As you can see, it's images of colonoscopy polyps, and each of the folders is divided to a ground truth images and original images. The original images are the polyp images, and the ground truth are the images of the masks that mark the polyp in the images. So you can download the dataset and extract it to a local folder. As you can see, I have done it already. And we are ready to start. So as I said earlier, these are the original images, and there is also the ground truth, which are the masks. The names of the files are the same, so each image has its similar name or identical name with its correspondent mask. I will leave a link for the dataset, so it will be easier to download it from your Kaggle website. We start by importing the necessary libraries. We will use OpenCV, NumPy, and OS. This will help us to handle images processing and manage the file path. Next, we define the dimensions of our images, the height and the width, to ensure consistency during the preprocessing. Now we specify the path for our datasets, including the original folder containing the images and the ground truth folder containing the corresponding masks. Okay. Let's take a look at the number of images in our dataset. This gives us an idea of the size of the dataset. Let's run the code. I have a syntax error. Let's fix it. Forgot a slash. Okay, so these are the names of the files, and we have a total files of 612. Now let's load one of the images and display it, and we would also like to load one of the masks and display it next to the image, so we will understand what is the process that each of those images will go through in the next phase. So we will use OpenCV to load one of the images named 1.png. Of course, it's a color image. Then we would like to resize it to our needs, which is the 256 by 256. Now let's duplicate it and do it the same way for our mask. As you can see, the name of the file is the same, it's 1.png. We only change the path for the images, and of course it's a grayscale and not 3 channels image. Now let's show both images, one next to each other. Let's run it. As you can see, this is the image and this is the mask, and the mask mark the polyp in the image. The next step is very important. We would like to understand the value inside each of the masks. Since the mask has the mask image is 256 by 256, we would like to temporarily resize it just to demonstrate what we are going to do for this mask. We're going to convert it to our needs. So just for now, we would like to resize it again to a dimension of 16 by 16, so we can print the value inside this very, very small and tiny mask image. Let's run it again. Okay, now it's better. As you can see, This is the 16 by 16, and you can see the values are between 0 and 255. So the values above 200, so above 0, indicates the polyp in the mask image. So we would like to do some transform or some change in the values. So basically all the 0 values will remain 0 and they are indicates the background, and all the other values would mark the polyp. So we would like to change the values to another value, for example a value 1 or a value 255. Let's decide it during the code. I believe it will be a 1, but let's define a threshold. So every value under 50 would be a 0 that indicates a background, and every value above 50 will indicate that the polyp for the mask. So we will replace it with the value 1. Okay. Let's run it again so we can see before and after. As you can see in here, we change all the values to 0 and 1, and it will help us with our model, since it will be a binary model. All the zeros are the backgrounds and all the ones are the polyp. So now we are ready to run a loop through all the images. So as you can see, we loop through each image file, resize it to our specific dimension, and normalize the pixels values between 0 and 1. All the converted images will be inserted to our list of images called all images. For the mask, we process them similarly, but we also convert the mask values into binary pixels. Pixels with the value less or equal to 50 will become 0, which indicates the background, as I said earlier, and pixels greater than 50 will become 1, which is the mask area that indicates the polyp. Once we process all the images and mask, we convert them into NumPy arrays for the compatibility with the TensorFlow. Now let's print the shape of the images and the masks, and to see the amount of the images that were inserted for both NumPy array. We will also print the type of those NumPy array. So one should be a float and the next one will be an integer. Nice. Okay. So we can see that we have 612 images. So we can continue for the next step. Now we split our dataset into a training, validation, and test set using the train test split function from sklearn. This will ensure that we have separated data subset for the training, validation, and testing for our unit model. So we'll divided this split process to two phases. The first one is creating a train and a test dataset. We will create a 90% for train and 10% for test. Okay, so now we will take our train datasets which have only 90% from the whole dataset, and we will split 10% from this train dataset to validation dataset. So now let's print the shapes of the trained, rest, and validation dataset. Let's run it. Okay, let's run it again after we fix this. Very nice. Okay, we've successfully preprocessed our data and split it to our necessary dataset. Now we would like to save this dataset for the next phase and for future use. So let's use the save function from a NumPy array, and we will save each of the dataset with its own name in our local folder. Okay, let's run it. Start the saving. It will take a few seconds and finish the saving. Let's look in our saved folder. As you can see, here are all the dataset. So now we are ready for creating the model. Now we will create a new Python file, and this Python file will be dedicated for building our unit model. We will split the process of building the model and training the model. We will start with importing the necessary Python libraries. Of course, we will import TensorFlow, and we will import from Keras all the layers, and we also import the model object from Keras model. Now we would like to define our convolution blocks. Let's open once again the image of the unit architectures, and you can see we have double layers of 64, double layers of 128, 256 and 512, and then we have the right side of the U shape. So let's create a function, basically to make our code cleaner and more modular. We defined a conv block function. This function applies a convolutional, batch normalization and a reload activation in sequence. So please follow this code, and as you can see, we are creating layers that each layer will get will build over its previous layer, and each layer is combined with convolutional layer, a batch normalization and a reload activation function. Okay, now it's the second convolutional layer. Another batch normalization and a reload activation. So basically it's a double of 3 layers, one on each other. And we will return this bulk of convolution layers. Now let's define a build model function. This function takes an input shape and constructs it to our unit model architecture. Before the coding, as you can see, the original unit is defined with these number of filters: 64, 128, 256 and 512. Since we would like that our model will run faster and won't consume a lot of memory usage, we will reduce this number to 16, 32, 48 and 64. You can use the original numbers, but for our tutorial, reduced numbers will be good enough. As you can see, we defined our model inputs using the input layer from Keras. We will pass in the shape of our images. Next, we create an array of number of filters to determine the number of filters in each layer of our model. We also initialize an empty list skip_x to store the skip connections. Now we are ready to build our encoder part, the left part of our unit model. We loop through the number of filters array, applying our conv block function, and adding each layer output to the skip_x. And we will also perform a max pooling to the down sample. After the encoding, we create a bridge layer of 128 filters to connect the contracting and the expanding path. Once again, we are reducing the number from 1024 to 128. And now let's set up the decoder part of our unit. We reverse the number of filters and the skip_x arrays to match the expanding path, and we will use the upsampling 2D to upsample the feature maps. During this process, for each layer in the decoder, we concatenate the upsampled feature map with the corresponding skip connections. These skip connections aid the precise localization. And finally, we add an output layer with a single filter for binary segmentation. This is the last layer. We apply a sigmoid function since we are dealing with a binary classification task. After this build model function is completed, we are successfully constructed our uni architecture, and we are ready to process to our next phase, which is training our model. So let's create our next Python program, and we will begin with loading the pre-processed data that we have saved earlier, our training, validation, and test dataset that are ready for action. So let's replace the saving part with the loading function, and of course duplicate it for all the other dataset. Okay, now let's run it. As you can see, we are printing the datasets, and that indicates that everything was loaded successfully. Now we will set the dimensions of our images, the height and the width, to ensure consistency during the training process. With our data ready, we can import TensorFlow once again and import the build model function that we defined earlier. But next, please notice that we have a problem. The name of the step 2 Python program has, let's say, call it a special character, and Python does not allow it using the import function. So we will rename the name of the step 2 Python program, and it will be only English characters. Now we will fix it in step 3, and you can see now that everything is green, and we can use and import the build model function. Let's also import from the callback class some more functions that we will use it in the training process, for example the early stopping. Now we will specify some training parameters, including the learning rate, the batch size, and the number of epochs. These parameters will influence and affect our model, how our model will learn. So now let's create our model variable using our build model function, and let's print the summary of this model and run it just to see that we have an empty model with all the required layers. As you can see, we have a problem with the batch normalization function. Let's go back to step number 2. As you can see, I have a syntax error with the name of the function. Let's fix it in both places, and let's run it again. Now I have another error, a problem with the shape. I forgot to add the reverse function. I have to fix it, and let's run it again. Good. As you can see, now we have the model with all the layers. So let's continue for the next step. Now let's create our optimizer. We will use, of course, the Adam function, the Adam optimizer, and we will use the argument of the learning rate. Next, we will compile our model. It's a binary model, so we will use the binary cross-entropy, the optimizer, the Adam optimizer with our starting learning rate, and the metrics will be accuracy. Now let's define the steps per epochs. In order to calculate this, we will divide the number of trained samples in our batch size. And we will do a similar process with the validation data. Let's create a file for our model. Our model will be saved under the temp folder with the name Polyp segment.h5. Now let's specify some callbacks in order to enhance our training process. That include a model checkpoint. We will reduce the learning rate on plateau, and we also use an early stopping process. The patient's variable is the number of how, let's say, what should be the amount of waiting before changing the the learning rate, and next for the early stopping as well. Okay, now we are ready for the training process. We will use the fit function to train our model using our training and validation data. As you can see, we are sending to this fit function the X-train and the Y-train. That means our train data, the batch size as we defined it earlier, the number of epochs, which is 50, and also the validation data, which is xval and yval. The last phase before running the training is we would like to visualize the accuracy and the loss, and we will use the matplotlib charts. These charts will give us insights into how well our model is learning. So we basically will create two charts, one for the accuracy and one for the loss. And in each of these charts we will compare the training accuracy and the validation accuracy, and of course the loss and the validation loss. And after the training, we would like to evaluate our model performance using the test data, which is a fresh new data that the model never seen it before. And we will assess both the accuracy and the loss to gauge how well our model generates. Okay, we're ready to run the code. And the first time, okay, we have an error. I can see that the matrix and the loss both has a syntax error. Let's fix the metrics, and now let's fix the loss, and let's run it again. We have another problem. It seems that like it's a problem with the shapes. Oh, I have to fix this. It should be a mask inside and not image inside. So the problem is that the mask has only one channel and the image has 3 channels, and this pop up this error message. So let's run the step 1, which is generating the data, and let's once again see if we have more errors. This one, the matplotlib, we have to fix it, and this one x, it should be in lowercase. I hope that is the last one, and let's run it again. Okay, we can see that the training stopped. This is the first epoch, this is the second epoch. You can see that each time that the loss is being improved, the model is being saved. Okay, it's running really fast. You can see also that the validation accuracy is very good as well. It's a 0.9. Oh, it's looking good. Each time that the loss is being improved, the lost value, the model is saved once again and again and again. That's improved. That means that our training is very good and it's being improved during the training process. 15 epochs, 16 epochs. Okay, let's wait for the end. I can see that it will take a few more seconds. Please notice that the learning rate was changed as well. That's very good. So you can see that the training was stopped after about 30 epochs. The training and the validation looks very good, and the loss, when we are comparing the training and the validation, looks very good. So now we are ready to test our model with a fresh new image. So let's create our fourth Python program. Let's call it step number 4, testing our model. So once again, let's import some Python libraries. We will import a NumPy array and TensorFlow. Next, we will import our saved model. First of all, let's copy the name of the file and its location, of course, and then we will use the TensorFlow load model in order to load our saved model into this model variable. And let's print the summary of this model just to double check that it was loaded successfully. Very nice. This is the structure of the model, so we can continue for the next step. Now we will also load our test data, both the input images and their corresponding ground truth mask. And this data will help us to assess how well our model performed. So now let's take one of the images, for example, image number 4, in the position number 4 in our NumPy array. And let's display and show this image. As you can see, this is a 256 by 256 image, so it was displayed correctly. And to prepare this image for prediction, we need to expand its dimensions. We will use the np-expand-dims function, and this will ensure it's the expected shape for our model. So let's, for example, print the shape before this function, after this function, just to explain it. So basically we are creating a batch of images, but those batch of images has only one image inside. So this is the previous shape, and this is the shape after the expand dims. Let's feed the prepared image to our trained model for prediction. We will run and call the predict function on our model and obtain the predicted segmentation mask. And the next process is explaining and understanding the results of the prediction function. And since our model is a binary classification model, we have to adjust the values in order to display the results. So we will run through the values of the results, and each value which is below 0.5, we will replace it with a zero value. That is for us a black color for the results, and any value above 0.5 we will replace it with the value of 255, which is a white color. So this will help us to visualize the result image, which is a new mask. So basically, when we are feeding our model with a new image, we are expecting a result of a mask that every white area we will indicate a polyp, and every black area will indicate a background. So now we will display our original image and the result mask. Let's run it. As you can see, this is the original test image, and this is our predicted results. Very nice and cool. As you can see, our model works perfect. Thank you very much. Hope you enjoyed this tutorial. You are most welcome to subscribe my channel. Bye bye.